Welcome to the Explainer. Today, we are going to look under the hood of a seriously advanced mathematical framework, one that aims to completely solve one of the most notoriously stubborn problems in all of mathematics, the infamous Collatz Conjecture. Now, for decades, mathematicians have tried to untangle this simple but wildly unpredictable arithmetic sequence. But today, well, we aren't just tracing numbers. We're going to look at a completely different topological approach.
Okay, let's drive right into this. Think about the traditional arithmetic approach for a second. You're basically tracing infinite, chaotic individual trajectories. Honestly, it's a bit like trying to predict the exact path of a single dust particle in a raging hurricane. But the Adelic Langlands program shifts the entire problem onto something called the two-adic units. This is a specialized number system designed specifically for handling these types of divisible structures. What it does is transform all that arithmetic chaos into a highly stable topological space. It maps the known 1-4-2-1 loop as the sole stable rational fixed point. So our overarching goal here is to prove, mathematically, that there is literally no topological space left for any non-trivial cycles to exist.
To demystify this proof, we're going to walk step by step through a four-stage tutorial, defining the cone, operator invariance, the Sobolev matrix, and finally, the trace formula contradiction. Think of this as our visual roadmap. It shows exactly how we'll build this mathematical engine, moving from establishing very strict analytical boundaries in step 1, validating the dynamics in step 2, quantifying the whole system in step 3, all the way down to a final undeniable contradiction in step 4. Let's get started. Stage 1. Defining the cone.
So, before we do anything else, we absolutely have to establish a stable domain for our analysis. We do this by defining what is mathematically known as an invariant positive cone. We'll just call it C for short. Now don't picture a physical traffic cone here. This is a strict mathematical boundary within a multi-derivative Sobolev case, basically a space that measures both a function's values and exactly how fast it changes. Its entire purpose is to keep our functions well-behaved and establish a strictly positive baseline for all the heavy calculations that are about to follow.
If you look closely at the actual equation building this cone, you'll notice three key components at play. The first part bounds the local mass, basically forcing the function to stay greater than or equal to 0. The second part restricts the first-order density variation, bounding it tightly to that local mass. But the real magic happens in that final piece of the equation, the weighted cone constraint. By enforcing a strict limit as x approaches 0 from the positive side, it actively prevents derivative singularities from destabilizing our boundaries. In plain English, it keeps the math from breaking down at the edges.
Moving right along to stage 2, operator invariance.
Now that we have our cone, we need to test the dynamics. We have to prove that applying the Collatz transfer operator to our cone C maps it right back into C. To do this, the framework rigorously verifies three specific conditions. First is mass invariance. Because the branch weights are strictly positive, the operator itself is absolutely positive. If you start greater than or equal to 0, you are guaranteed to stay there. Next up is variation contraction, and finally, singularity neutralization. Let's dig into how those last two are actually achieved. By utilizing two-adic Glossoda-Yorke contraction properties, the operator mathematically forces the derivative contraction multiplier to be less than or equal to 2/3. When spatial partitions are scaled to be greater than or equal to 2 cubed, something pretty remarkable happens. The local density distortion is just completely crushed. This is absolutely crucial because it guarantees that the output variation remains bounded and never, ever outpaces the mass. And this elegantly sets us up to handle the third condition. You see, the derivative of the weight function naturally wants to spike right at the origin as y approaches 0. But by utilizing a brilliant two-adic coordinate transform, this step shifts that dangerous singularity completely away from 0. It maps it safely onto a stable interior fixed point where x star equals -1/3. Because the function at -1/3 is strictly finite, that terrifying boundary spike, it's entirely neutralized.
Okay, stage 3, the Sobolev matrix.
Now that our boundaries and our dynamics are totally rock solid, we need to quantify the system to compute its spectral properties. We do this using a beautifully structured 3x3 block triangular majorant matrix, which we'll call K. It tracks three really important elements. Block A manages localized mass transport, ensuring our two-adic volume is conserved. Block B tracks the variation contraction, which is essentially the first-order density stretching. And Block C, that governs our second-order curvature and oscillation.
The most crucial takeaway is in the core of this equation. Because matrix K is strictly lower triangular, its global spectral properties are completely dictated by that top left core mass block, block A.
The math simplifies in such an elegant way here. It means that once our spatial partition thresholds hit our set limit, the localized mass contractions seamlessly absorb those wildly expansive 3x plus 1 arithmetic steps.
To prove this beyond a shadow of a doubt, a computer-assisted Krawczyk operator steps in. It verifies strict inverse positivity, proving that the inverse of the identity matrix minus k is greater than or equal to 0. Think of this as a mathematical padlock. It guarantees that the global spectral radius falls strictly below that critical threshold of 1. And because of this, all subdominant eigenvalues are mathematically locked into an irreversible exponential decay.
Which brings us to our grand finale. Stage 4. Trace formula contradiction. That exponential decay we just talked about, it sets up the ultimate mathematical showdown, where we pit spectral limits directly against geometric limits. To do this, we bring in a true heavy hitter, the Arthur-Selberg trace formula. This is a master equation, and it forms the entire battleground for our final proof by contradiction. It demands a perfect, unwavering balance between two completely distinct ways of measuring the system. Let's look at the formula itself. On one side of this equation, we have the spectral eigenvalues of the Collatz-Hecke operator, and on the other side, we have the geometric orbital integrals. For the mathematics of this framework to hold true, these two sides must balance perfectly. They have to equal each other.
So let's break down what actually goes into that geometric side of the equation. The trivial path, which is our well-known 1-4-2-1 cycle, contributes a mathematically contractive weight of exactly 2/3 at each step. But here is the non-trivial hypothesis. If some unknown rogue cycle of period n actually existed out there in the chaos, it would be mathematically forced to inject a fixed, strictly positive geometric volume weight into the equation.
But watch what happens to our scales as we take the limit as the trajectory length approaches infinity. Remember our Krawczyk certificate from earlier? Because our maximum eigenvalue is strictly locked at less than 1, the limit of the spectral trace collapses to exactly 0. However, if that non-trivial cycle existed, its geometric volume on the other side of the equation would remain stubbornly, irreversibly positive.
And boom! Right there is our fatal mathematical contradiction, laid completely bare. 0 on one side of our equation absolutely cannot equal a strictly positive geometric limit on the other side. The equation breaks, the balance is quite literally impossible.
The final mathematical verdict. This absolute mathematical impossibility brings us to our conclusive verdict on the Collatz conjecture within this framework. Because that spectral limit completely collapsed to 0, the spectral gap leaves absolutely 0 mathematical volume for rogue trajectories to exist. By translating the arithmetic chaos into this stable topological space, the math literally suffocates any possibility of unknown orbits. No non-trivial periodic orbits can exist. The 1-4-2-1 loop stands entirely, undeniably alone.
This explainer brilliantly illustrates how simply changing our mathematical perspective, moving from tracing individual arithmetic steps to looking at a sweeping topological landscape, can solve the seemingly impossible. It goes to show that within the right mathematical framework, chaos is really just structure waiting to be defined. Which leaves us with a pretty fascinating thought to take away. If these kinds of mathematical constraints can completely tame the Collatz sequence, what other chaotic mysteries in science and math might be hiding perfectly balanced topological solutions, just waiting for us to change our lens?